Today on Signal Galaxies Unlimited, we continue our discussion on polyphase filters. Let's do a quick review from where I left off after the last video on talking about polyphase filters. I finished up with this flow graph creating a low-pass filter based on polyphase filter bank. And what you start with is you start with a stream demux that does the downsampling, where I've divided it up into 12 channels. I'm starting with a sample rate of 2.4 megs, dividing it into 12 channels. Each channel, therefore, is going to be 1/12 of that 2.4 megs, or 200 kilohertz. Each one goes through a set of filter taps based on a standard low-pass filter for this particular range. In this particular case, I used a low-pass filter with a 90 kilohertz cutoff frequency and a 10 kilohertz transition width, due to the fact that 2 times that is 200 kilohertz, which matches the 200 kilohertz channel width. The output of each of these filters still contains all of the original spectral information. It's not until you get to the output of this add block here that you wind up with everything adding, subtracting, canceling out, constructively adding, and so on, that you finally get the actual output product, which in this particular case, because I used a low-pass filter, is going to be the signal at the center of the spectrum. Let's take a look at that. When I fire up this particular flow graph, here is my original spectrum, and specifically I have the low-pass filter set to get the signal here in the center. All of the other spectral energy will be filtered out. When you've done the decimation by a factor of 12, you've effectively made 12 channels inside of this 2.4 meg spectrum. All of the energy of the other 11 channels will still be aliased down into this center channel. This is actually technically called channel 0, and that channel 0 energy will be still much greater due to the fact that all of the other energy will be seriously attenuated. So even though everything is going to be aliased down into this channel 0, due to the fact that all of the other channels will be seriously attenuated, the total energy will still be negligible compared to this signal here. Therefore, we effectively have just this one signal here in the center. So far, so good? Okay, let's continue on. Considering the fact that when you look at how we have done the filtering, saying that we have taken all of these other 11 channels and aliased them down into this center channel, there's no reason why we can't go ahead and set up a filter to say, hey, just filter a different channel, and when it gets filtered or gets aliased down into that center channel, that will be the signal that we will be collecting on. This is going to be the basis for the bandpass filter that we're about to create. What we're going to do is we're going to set up a bandpass filter. Specifically, just to start with, I'm going to use this signal here centered at -1 megahertz. And we're going to build a bandpass filter to filter this particular signal. And with that, everything else will be attenuated away. And when it gets aliased down to the center channel, it will be the only remaining actual energy. Therefore, it'll be the signal that we'll be able to recover. The way that I'm going to do this in this particular case is I'm going to take the original flow graph here. I'm going to take this low-pass filter taps, which creates my prototype filter. I'm going to delete it. I'm going to come up here. I'm going to add in a bandpass filter taps block. Open it up. I'm going to start with its ID. I'm going to go ahead and say the exact same ID as before, prototaps. The tap type is set for real. What that means is that if I use a tap type of real, I'm going to have the same frequency limits between the negative frequencies and the positive frequencies. I don't want that. I want it just one-sided, just in this particular case, just for specific negative frequencies. To do that, I'm going to have to change this from real to complex. Next part, for the low pass frequency and the high pass frequency cutoffs, or the low frequency cutoff and the high frequency cutoff, what I'm going to set is I'm going to say my center frequency for the signal was -1 meg, And so I have to, for the low frequency, subtract 90 kilohertz from that. So I'm just going to make this easy. I'm going to say minus 1090 kilohertz. So basically 1090 kilohertz for the low frequency. And then for the high frequency, I'm going to add 90 kilohertz, which from 1 meg, which means it's going to be 910 kilohertz. And the transition width is the same as before. With these particular values, and the fact that I'm using the Hamming window, which is what I was using for the low-pass filter, under the low-pass filter, and the transition width of 10K with a 2.4 meg sample rate, the number of taps that I'm going to use is going to be identical as what I had with the low-pass filter. The only difference is that the low-pass filter was real taps, whereas this is going to be complex taps. So they're probably going to be a little bit more calculation involved due to the fact that I'm using complex versus real. However, that depends on how your system is actually doing the complex, doing the actual calculations when you're doing mixing real and complex. Anyway, the number of taps is going to be identical, meaning that as far as the system is concerned, it's really not a whole lot more processing involved. Everything else stays the same. All I've done is I've changed the filter taps for my prototype filter. The rest of this flow graph will divide them up into these 12 FIR filters in my filter bank. Once it gets over here to this add block and everything gets added together, the various parts, you get constructive and destructive signaling going on here, meaning that what's going to happen is the only energy that's going to be left over is going to be that signal at minus 1 megahertz. And when it gets aliased to channel 0, like all of the channels will be, it will be the only actual energy left, meaning that we will be left with that one signal. Let's take a look. Here is my original spectrum. Again, this is what the signal here that I'm going to be looking at. Here's my filtered spectrum, which is kind of hard to tell, but this is actually the filtered spectrum of this signal here at minus 1 meg. And to really see it, what I've done is I've gone ahead and created a demodulated spectrum, and this is the demodulated spectrum, which, when you remember, for my original low-pass filter, that signal there at channel 0, I did not have that an SEA spike like I do here. In this particular case, this is 90.9, which is WETA in DC, and it has an SCA at 67 kilohertz. It used to be reading for the blind, has not been active for several months now. Don't understand why they still have it turned on, but anyway, we can use this as an identifier, saying, yep, there's nothing here. There's an SEA here, whereas none of the other channels have that. Therefore, yeah, it's definitely the right channel. That means that we have effectively, just with that change alone, we have made a flow graph with a decimating filter that's doing three things. First, it's downsampling with this demux. The filter bank, it's doing the filtering as the filter bank along with the addition here. And due to the fact that I'm doing the downsampling as well, it also, due to the aliasing, it has also done a frequency shift. So again, I've done downsampling, I've done filtering, I've done the frequency shift, all with this particular flow graph. I'm going to make another minor tweak to my flow graph. Specifically, I have added a QGUI range variable, and this particular variable gives us values, integer values between 0 and 10. What I'm going to use this is to be able to select different channels. From that, it's going to go into my bandpass filter tap calculations, where I'm actually going to calculate based on the channel number and the channel spacing of 200 kilohertz. I'm going to be able to select different channels. When I choose a different channel, it's going to come in here, set the new low and high cutoff frequencies, which will then calculate new taps. That will then get promulgated to the different FIO filters in my filter bank, and therefore allow me to effectively select different channels just based on that. When I look at this, I start at the way I have it numbered is channel 0 is the -1 megahertz, and then I just go in 200 kilohertz steps. can most easily see this in my filtered spectrum. So again, this is that -1 megahertz signal. Here is the second one, which is just a IBOC plus blank space. Another one, blank space, and another IBOC. And as I keep going up, I'll eventually get to other channels. But with this, just by changing those tap values, I can select different channels within the spectrum. And again, all I'm doing here is with this one flow graph, I'm effectively downsampling. That's with a stream demux. I am filtering with the filter blank plus the add block, and I'm frequency shifting just due to the inherent aliasing when I do the downsampling. So all three of those things with this one flow graph, and again, all I'm doing is I'm just going in and changing those tap values, getting fed into the system, which then just continuously does the new calculations and allows me to select the different channels. Now again, every time I'm doing this new selection, it's still all of the channels inside of my spectrum here are getting aliased down into the center of my spectrum. That still happens. It's just that with those different filter taps, it's allowing different channels to essentially be the strongest signal. Everything else gets attenuated away. Let me do a quick digression here to make certain that you understand the drawbacks of this particular type of filtering. So in other words, if you're going to use a bandpass filter and rely upon aliasing in order to be able to do the downshifting, then what you have to understand is, first off, your signals have to be spaced equally apart. In this particular case, I'm looking at FM broadcast stations here in the US, which are 200 kilohertz apart. Therefore, my spacing my channel width is going to be 200 kilohertz. Next thing, my sample rate has to be an integer multiple of that channel spacing. In this particular case, I'm using 2.4 megahertz sample rate, which is 12 times my channel spacing of 200 kilohertz. That's the reason why effectively I said, okay, I'm starting really at 200 kilohertz channel spacing, and with a factor of 12, that gets me 2.4 megs, which is within the capabilities of the RTL-SDR. I can't go to 2.6 megs because that's when you start getting drop samples with the RTL-SDR. 2.4 megs is really the only value that makes sense for this particular case. Therefore, again, have to be equally spaced apart, and the sample rate has to be an integer multiple of the number of channels that you're going to collect. This brings me to the last part of the video, in which I'm going to take this particular flow graph where I've made a bandpass filter, allowing me to select each channel individually. In other words, do it one at a time and transform it into one which gives me access to all of the channels at the same time. This is going to be a polyphase channelizer that I'm going to make. First thing I need to do, this bandpass filter, I need to change it back into a low pass filter. What I'm going to do here is I'm going to come up in and I'm going to say low. I'm going to select the low pass filter taps, and I'm going to use the exact same values that I had before. This will be proto taps, cutoff frequency of 90 kilohertz, transition width of 10 kilohertz, Hamming window and all. And now it's set and ready to be changed. But understand again how this works. I'm decimating or downsampling with the demux. Each one of those downsample demux goes through a slightly different set of filter taps. And then when it gets over here to the add takes everything, sums it all up such that due to all of the various phasings of the different parts of the signal, the parts that are outside of the band will cancel away, and the parts that are inside of the band will effectively add together, so I'm left with that one channel. The difference is that if I can take this and shift this addition to after I have multiplied each of the channels by its own complex sinusoid, in other words, do a frequency shift, a complex frequency shift, then I can get access to all of the channels at the same time. What that's going to require is, let me first off not get rid of these, but just kind of move them off to the side, get them out of the way. I'm going to take this add block and I'm going to delete it. And then I'm going to take the filter, and I'm going to add in a mux block, a stream mux block for its particular values. I'm going to say the length is just going to be a 1 multiplied 12 times, so that I wind up with a vector of 1. So I can just see that real quick. There I can see the value is just a vector of 12 ones. And then the number of inputs is going to also be 12, which is DEC. And the difference is between the demux and the mux is that the demux I have 0 going to 11, 1 going to 10, and so on, whereas on the output 11 is going to go to 11, 10 to 10, and so on. Let me do that real quick. I now have the streams muxed back together, multiplexed back together, such that I'm winding up at the output here with a 2.4 megasample per second sample stream. However, I'm not going to treat them as individual samples. I'm going to treat them as blocks of 12. 12 is, again, that's my downsample or decimation value. To treat them as blocks, I am going to first add in a stream to vector block. Change its number of items to DEC. And then I said that I'm going to need to multiply by a complex sinusoid for each of the individual channels and then add them together. There's a block that's already set up to do that. It's called the FFT block. That's what you're doing. You're multiplying by a complex sinusoid and then adding everything together. The difference is that in this particular case, I'm not using 1024, 2048, 8192. No, I'm just using 12, which is my DEC value. I'm also not doing a forward, I'm doing a reverse FFT. Next part is I am doing a window. I'm just going to normalize the values. I'm going to do a open bracket, 1 comma, close bracket, times DEC. That should finish that off. That's now set and ready to go. At the output here, I'm now ready to turn it back into individual sample streams. So for that, I'm going to use a vector to stream. And then the last part is I'm ready to now demux them or pull them out into individual streams. Well, guess what? I've already got a block doing that, and it's even got the right values to do it. So I'm just going to highlight this block, Control C to copy it into memory, Control V to paste it, connect it to the output here, and each one of these outputs is an individual channel. Now, here's the part that you have to understand. Channel 0, when you look at my spectrum, my original spectrum, and the way that it's channelized, this is my 12 channels. Channel 0 is this one here in the center. And so this would be 0, 1, 2, 3, 4, 5, 6 straddles the two ends. 7 is the one that I was saying, yeah, that's the one that I really want to start with over here on the left end. So this would be 7, 8, 9, 10, and then 11 is the one just to the left of center. If I want to keep that kind of channeling that I had before where I said this is actually channel 0, well, I need to make an adjustment. And so what I'm going to do is I'm going to put in a selector. And the particular selector that I'm going to use, first I'm going to say the number of inputs is going to be DEC. Number of outputs is going to be 1. And then for the channel, for the input index, meaning selecting which channel I want, well, I already have this range block up here, this QGUI range block for the channel value. I'm just going to go ahead and use that. Everything else should be good to go. However, before I do the connections, let me explain that in this range block, I need to open it up. I have the type set to float. I'm going to change that to integer. The reason being is that in here, it wants this value both the input and the output index to be integers, not floats. Otherwise, it's going to throw kind of a fit. Now, as I said before, when I'm looking at the spectrum, 0 is this one here at the center. This is actually channel 7. If I want the outputs to kind of match up where it says this is 0 and 1 and 2 and 3, I'm going to have to make the connections where here is 7, that goes up here to 0, and then I just keep those until I get to here to 11, and then once I start back here at 0, I just keep on wrapping around. And finally, I'm just going to make my final connections to my demodulator and frequency sync to show my baseband spectrum as well as the channel spectrum. If I run this, and before I do that, let me go ahead and make some changes here. This is going to be channelizer, and then I'm going to call this the polyphase channelizer, and I'm also going to do a save as, and I'm going to call this the polyphase channelizer. And let's run this and let's see what we get. Here's my spectrum, my original spectrum, and again, I should be seeing, if I have everything set up right, I'm on right now on channel 0. That should correspond to this signal here the way I have it set up. Let's take a look at our filtered spectrum. Maybe it's kind of hard to tell, but the baseband spectrum, oh, guess what? There's that 67 kilohertz SCA. So yes, I have that set up right. If I have this, again, if I have this set up correctly, channel 1, which corresponds to this channel here, should have a fairly large IBOC and then a flat spectrum. So let's take a look. We're going to come over here. Yep, there's that IBOC and then flat spectrum and then flat spectrum and another slightly shorter IBOC. So let's take a look. Yep, that's the case. So yes, this one here corresponds to this channel here, and so on all the way up. So again, if I were going to be using a polyphase channelizer block, if I were going to use the polyphase channelizer block, these connections are what you're doing with this channel map value down here. In other words, I could set this up to say 7, 8, 9, 10, 11, and then start back at 0 through 6, and that would do the exact same thing as the way that I have these connections here. Final little bit that I want to do for today is a comparison between this polyphase channelizer that I built from basic components and compare it to the actual polyphase channelizer block. What I've done here is I've taken this particular flow graph and I've taken out everything from the stream demux all the way over to this stream demux over here. So everything in between I've gotten rid of, I've deleted, and then I've dropped in the polyphase channelizer block. When you look at the particular values, so again, your taps, well, that's just these proto taps that I was using before. Ignore the oversampling ratio and the attenuation and the sample delay. The last thing that you're really going to be concerned with is this channel map. And remember I said before that when you look at my original spectrum, this is coming out of the vector to stream. This is effectively channel 0 here, is the one in the center, then it goes 0, 1, 2 on up. This is channel 7. So what I said in my channel map was I said, oh, I want channel 7, that one there on the left with the 67 kilohertz SCA, I want that to be the first one in line. So I've made that the first one here in the channel map. I've said, okay, take output 0 and make that 7. Okay, so I got 7, 8, 9, 10, and then I wrap around back to 0 up through 6. And let me also make an adjustment here. We'll make this channel up to channel 11. And if I run this and look at its outputs, again, if I've got everything set up right, well then first off, the filter spectrum should be this guy here. It pretty much looks the same as it did before, but the real tell is here. Well, yep, there's the 67 kilohertz SCA, so I've got that right. Also, if looking at here, The next one in line should be this IBOC with a flat spectrum. So if I look at that, yep, sure enough, IBOC flat spectrum, followed by flat spectrum, slightly lower IBOC, followed by another FM station, which should correspond to this particular channel right here. Finally, when I get up to channel, let's see here, this is 0, 1, 2, 3, 4, 5 should be the one here in the center. So if I go up to 5, should be, yep, there's an FM station there. Yeah, that looks pretty much like it did before. So that is my center station, and so on. So what we've done, what I've done here to demonstrate is showing you essentially what is going on inside of this channelizer block. Now, is it absolutely identical? No, it is not. There's other, I'm sure there's other little subtleties going on in there, especially the way that I've done the padding to create the actual taps and so on. But regardless, this should be pretty much good comparison between what this Polyphase channelizer block is doing and what I've demonstrated here building it from basic components. With that, wraps up my discussion on polyphase filters and polyphase filter banks. My next video will be on infinite impulse response, or IIR filters. That will wrap up my digital filtering, and that should be a good day's work for anybody. Till then, hope you all take care, and I will see you later.